to graph. When you first learned how to graph equations, no matter what it was, you guys always made up a table set of values. Remember that? Whenever you first started graphing, you had to graph the line y equals x minus 4. What you did is you picked numbers to work with. Let values of x go -2, -1, 0, 1, and 2. You did all of that long time ago. That was how you first initially learned how to graph things. You picked numbers that were easy, you plugged and chugged, and then you plotted them on a graph and went. That's generally how people learn how to graph. Then you learned the shortcuts. You learned stuff about y equals mx plus b. You learn how to walk with slopes, learn how to do other things. We also did that if you start thinking about when you got into stuff like this. You still did the same thing. You picked easy numbers. You looked at what was happening to the equations around the origin. What was happening on the positive side, what happens on the negative side, so you get a visual representation. You picked numbers that were always easy to work with. None of that changes when we go to that. But what you're going to change, though, are the numbers that you pick. You always want to pick numbers that make sense. When you want to pick numbers that make sense, if I wanted to graph the square root of x, well, what are perfect squares? Chad, put it away.
1, 4, 9.
Well, what's the first one?
0.
0. 1, 4, 9. You pick numbers that make sense. You pick numbers that are easy to manipulate, because am I going to let you use your graphing calculator to graph these things? No, because there are ways to do all of this without the use of technology. By using numbers that make sense. By learning how these graphs look in a generic sense, and then how do you manipulate them to shift them horizontally and vertically. So guess what's going to come back? H and K. There's going to be an A value. An A value is going to be a scalar, the whole deal. So if I go back and I start thinking about 0, 1, and 4, well, what's the square root of 0? 0. What's the square root of 1? What's the square root of 4? And the square root of 9. So on a piece of graph, and I actually have some graph paper here for you. I'm just going to start this right now. The generic form of a square root function is 0, 0, 1, 1, 4, 2, 9, 3. And it always has this curve to it. A square root function will always look like that. What changes is what the value in front of it does to it. An A value. Is there a scalar thrown in? Is there something along those lines? But it all starts from picking numbers that make sense. Getting values that are easy to work with, and then moving them if you have to. Okay? So when we get into the whole idea of graphing square roots and things, what I want to look at, I might as well just jump right in and doing some shit things with you guys. It's fun. Look, I made graph paper. I did. I'm like, I am nothing but the nicest person you guys will ever meet. Sorry, I didn't throw it. So,
look, I'm a nice guy. I'm giving you paper. You're just gonna
let's do this.
You just call yourself a nice guy.
nice guy. So thank you. Yes, and thank you, Betty. I'm here. Thank you.
Not for you.
You're so mean.
If it was anybody else, I would.
You're such a diva.
I'm just going to go jump right into the idea of graphing.
You're such a diva. See your phone case.
Square root stuff.
It's diva.
It does not say diva.
Tell me like a picture of you.
Yeah.
Diva. But you freaking bully me. put this up, says he's gonna put this up, and then just throw it back in your face. Yeah, I have to put this up, otherwise you'll bully this.
I do not bully you.
He's that you're talking trash, he's probably right now.
So let's use this generic form, and I'm going to show you this two different ways. When you're taking a square root function, again, we have this a, h, and k value. One of the things that will tend to happen from time to time is that sometimes they'll write it out in a generic form like this, or you might see it as k plus a root x minus h. They might put the k in front. The reason that they do that is so that way you guys don't accidentally think that the k value is underneath the radical. Yes, sir?
The way to stop yourself from doing that is just put parentheses around the root.
True, that's one way of doing it, but the books and things don't do that, so sometimes if you see it, you might accidentally go through it. It happens a lot, so the k value sometimes floats to the front or the back. It just so you guys are aware of it, it's kind of common that it does that a lot. Just remembering that that is your k value. So your a value, think of this as a scalar. Your h value is your horizontal shift. Gee, that looks familiar.
Scalar? Yeah, what does that mean?
No, not like scales on a fish. A scalar multiplier is if you have 2 times the square root of x. When you went through, we had those values of 0, 1, 1, 4, 2, 3, 9. What it's going to do is take, if x is 0, well, it's 2 times 2 is 0. If x is 1, it's going to become 2. If it's at 2, it's going to become 4. If it's at 3, it's going to become 6. It's kind of like it increases the rate. I believe so. A scalar multiplier, I believe, is 2 a's. Hey, Google that for me, would you? Is it scalar for scalar multiplier? I'm pretty sure it's AR.
I didn't think it's you.
No, I'm pretty sure it's AR. I'm pretty sure it's AR.
This is math, of course.
It is.
Trap, tell me I'm right, please.
You are right.
Yes!
What?
I am right.
How is it spelled?
IT.
What's that?
She just asked how is it spelled? IT.
How is it spelled?
SCALAR. And then K is going to be your vertical shift. So what we're going to do here is we're going to plot a generic graph. Pretty much the easiest thing to do is to plot a generic graph, take the 4 points and shift them. To be honest with you, that's always the easiest. But there's other ways of doing this as well. So what I like to do sometimes is one of 2 ways. I like to do what I call, by plotting the parent function, that would be, if it's just square root, just be the square root of x. The shifted function would then just be with the AH and K shifted into it. So there's a couple ways of going about it. Let's look at an example of, we okay? Can I go to the clean one?
Yeah.
All right. Excuse me. What did I have? So a lot of times what the book or worksheets or things tend to do is that if your K value is negative, they usually put it at the tail, but if the K value is positive, they usually put it in the front. They bounce it around a lot of times. It's no reason, it just does. So when I see these things, I kind of get like really oversimplified with it. And I know that I don't need to take as many steps as I do, but I always like to list what A, H, and K is. That way I know what direction things are going to go, so when I start to plot my true function, I know if I'm doing it right. Okay. Second semester, when we get into A, H, and K's again with logarithms and exponential functions, trigonometric functions, and all that, H and K's are still going to be there, and they all have to serve the same purpose, how things are shifted. But if you understand where things are being shifted, especially when we get to trig, you're going to understand the periodicities and the and things like that a lot easier. Period, time function that something occurs. Periodicity is just the multiples of them. Come on, it's English. I make myself sound smart today. A is 3. What's H? -2. And what's K? So that means right off the bat, what direction am I going to shift my original graph, my parent function? It's going to go down, and it's going to go what direction? Left. So I know that this means it's going to have to move left, and I know it's going to have to move down. So the reason that remember, it's x minus h. So if it's x minus h, it's always, whenever you see that minus value, it's always going to be opposite sign. It's usually minus h, and then it's just plus a k. I think the only other time that it was different is when we had the conic stuff, where it was always quantity x minus h, x minus k. I think it's the only time that you see a k value that's a minus. Everything else is a plus tag. Okay? So we do the same basic idea. I know that I'm going to take my parent function, I'm going to pick out very generic numbers of x, 0, 1, 4, and 9, because those are my first sets of perfect squares. I know that my root x for my parent function will be 0, 1, 2, and 3. I know that's what it's going to look like, because that's what all square root graphs start as. What then I do is I start to look at plotting. Now, when we did parent function, we did a parent function a long time ago, I think, right? We did it as a dotted line, and then our real one would be solid. What was that we did that with? Was that? No, we also did something else with. We did something else with parent function. So I plot it 0, 1, 4, 2, 9, 3. Your parent function is there just to help you visualize the general direction of where it should start at. I know that the parent function of 0, it's not technically there, so I just kind of know that it's going that way to begin with. Sometimes when you work with the parent function, it is also easy to automatically use your scalar to it before you do any shifts. Because if you think about your order of operations, well, let me rephrase that. This is going to be 3 times the x plus 2 minus, and there's minus 4. Now, this is where things get a little interesting. What you're doing here is thinking about what are you doing to each of these values of x. Now, I know that this one's going to have to move left 2. That's what it says to do. But is that going to help me with anything? Now, actually, let me rephrase that. When I move that parent one to the left, to -2, that means I'm picking a new value of x. I'm saying x is at -2. What's -2 plus 2? 0. What's 0 times 3? What's 0 minus 4? So I took this point, I moved it left 2, and I went down 4. Okay. I do it again. I move this one 2. Okay. Now, when you start moving things around, you're going to start seeing that, hey, this might be kind of goofy here. Well, let's think of this. When we have, I'm trying to make this work so you guys can see this easier. Watch this, just because this is the first one. Let me clear this out again. What was our original was square root of x? Let me show you how this looks if you do this in here so you can kind of get an idea. So you have 3 root x plus 2.
Yeah.
Then you hit the right button and then minus 4, right? When you go to your table, when you start looking at tables, you can kind of see how the original points move, okay? The idea here is, as you're taking numbers, oops, sorry. You're taking numbers that are making this shifted out thing workable, if you will. Buongiorno, como se va?
Je ne sais pas.
Au revoir. Good. You guys know I speak French? I'd say I'm good at it when I speak it. What? Can't they speak more than one language?
No.
So what this is doing, so +2. What this is doing is that it's creating values underneath the radical that are making it equal to the original parent ones. It's picking numbers that make it work. Because if I wanted to get a 0, well, how do I make a 0 underneath the radical? Well, I have to pick -2. At -2, I get square root of 0. 0 times 3 is 0. 0 minus 4 is -4. That's why that works. If I choose -1, -1 plus 2 is 1. The square root of 1 is 1. 1 times 3 is 3. 3 minus 4 is -1. What it's doing is that it's taking these values, by moving this to the left, it's saying start at -1. Well, at -1, if I substitute in, oops, this is -4, it's telling me to move it to the left from the parent. -1 plus 2 is how much? 1. What's 1 times 3? 3 minus 4 is? -1. So at -1, because I moved left, then I moved down, what did I say it was? At 1. Okay? It's telling me where things are going to go. I'm moving them around. Okay? I'm moving them around and I'm putting in my scalar to it. I'm picking the originals and I'm just kind of using them by shifting them to the left, resubstituting in, and can go. Okay? Watch again. The next number that worked here was what? At 2. The reason why 2 worked is because your parent function said 4. Well, if I move my parent function to the left too, I start there, because that's what this said to do. If I take it at 2, what's 2 plus 2? 4. What's 4 times 3? 12. What's 12 minus 4? 8. So my next point then was at 2 and 8. So this scalar is just making it increase faster. That's all it's doing. Okay? You're taking the basic parent function and you're just moving it, the h value first. Then you bring in the scalar. Okay? Now, sometimes it can be a little bit easier if you put the scalar in as part of the parent function, because you'll know how fast things are increasing right away, so you can kind of work with it, so it might be a little bit easier to visualize. Let me show you that real quick. If I do this a little bit differently.
Wait, Mr. Murphy.
Yes,
How
ma'am.
do you get 8?
How'd I get 8?
Aren't you supposed to, isn't it square root of 4 times 3? Oh, 4 times 3 is 12.
Wait, did I say?
Wait,
I
no.
can take the square root of 4. You're right.
I know,
I
that's
didn't
why I was
I'm
like,
sorry.
oh.
Yeah, I'm sorry. I didn't take the square root of 4. So it's 2. So 6. So
So
yeah.
6.
Sorry, I went up too fast. My bad. So what do we say? It was 2. 2 plus 2 is 4. Square root of 4 is 2.
So then
3 times 2 is
So
6.
it's 2. 2, 2.
Sorry about that. Let's see if we can do this and not screw up on. Let's see if I can do this and not screw up on 9. 9 minus 2 is 7. Oh, 9. Yeah, because I moved it left. Because then,
So X would be 7, right?
I don't know why I'm using this one, because then that one doesn't work as cleanly, because then you don't get a nice root anymore, which is fine. As you start going through, because then if you have 7, so we go 7 plus 2 is 9,
Yeah.
the square root of 9 is 3, 3 times 3 is 9, 9 minus 4 is 5, okay. So then at 7, we move left, and we're at here. Okay. Let me show you how this could be, probably be a little bit easier if we throw the scalar in right away, instead of trying to go off just the zeros, off the 1 ones. So let's show you this. What if we do it this way? Let's say that that's our parent. Okay? We'll throw the a value in, which is 3. Instead of putting the scalar in later, we'll put it in first. If we do it this way, oops. My y's look like x's sometimes if I get too fast. So we do the same idea. We have 0, 3. Oh, this is, I was thinking square roots in my head. This becomes root 4, 2, so this is 6. Root 3, which is, and this would be 9, correct? So if I plot that as the parent, by putting the scalar in right away, we go like this. We go 0, 1, 3, 4, 6, 9, 9. Okay on that?
Wait, that's, you said that's the scalar?
That's with the scalar. I'm going to try and show you guys this. There's 2 ways of plotting these things through. You can plot it with the 0 and then move things to the left and then multiply it out. But now if you already have them multiplied out, it might be a little bit easier. Bless you. Because now with these, what these plotted through, that's already got the scalar thrown into it. This might actually be a little bit clearer. I thought you guys would see, when I was doing it the other way, I was trying to get you guys to get the number sense of why things were moving and bumping up. But I think it might be a little too much mental math for a Wednesday at 9 o'clock in the morning, which I guess is not good. So if we throw the scalar in as your initial points, it might be a little bit easier to see, because now all you have to do is move them left and down. Left 2, down 1, 2, 3, 4. Left, oh, forgot to do this one. Left 2, down 1, 2. I did that one. 1, 2, 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. There it is. There's your shift. Let's do it that way from now on. That was a lot less stress on your brain, wasn't it?
Where did you get the, oh wait, is this the same problem?
Yeah. I was going to show you how I did it mentally with just the 1, 4, 0, 1, 4, and 9 as square roots. But then I realized by the glazed over lookages that I was getting that it might be a little bit better if I initially put it in with the scalars. So I thought I would try it, see if you guys could go for it. So it's okay. It works either way. Hey, guess what? This way's easier.
How do you get like this crash just take away 4? I get where you get the negative 2 and the negative 4 from.
That's your HTK, that's your horizontal shift. What we've done here, Trap, is that I've initially graphed a parent function with the scalar.
What do you do with the rest of it then?
What do you mean?
Like the plus 2 minus 4?
Remember how this was left 2 and then down 4?
Oh, that's all you're doing.
Yeah,
Yeah, but then you still have to multiply by 3.
I did that with the initial.
So you just take those numbers in the middle and move it left instead of down 4.
Oh, yes.
What?
Okay.
Oh, it was the same problem, that's why.
let
Yeah,
me
that's
do
how
it.
it's
Let me do another one, okay? Let me do another one. All right. So let's say we have this: y equals 2 square root x minus 3, and then we'll do plus 1. Okay.
So then the scalar would be 2 root x.
Yes. So I think it might be cleaner, instead of trying to get you guys to understand, well, to do a lot of mental math, which kind of backfired, to say the least. So we go through the other way. Let's plot out the y equals 2 root x. And we're going to use those values of x again, 0, 1, 4, and 9, because these are perfect squares. So if I do that with the 2 root x, I'm going to get 0, 2, the square root of 4 is 2, 2 times 2 is 4, square root of 9 is 3, 3 times 2 is 6. So these will be my parent function ordered pairs. Whoa. These will be my parent function ordered pairs. Are you okay with that?
So the parent function is just the x.
Yeah, with the scalar, and then we'll shift it. Okay, we'll do it that way. So now we have 0, 0, 1, 2, 4, 4, 9, and 6. And I hid the problem. It was minus 3 plus 1. So what do I have to do to all of these?
Subtract 3 plus 2.
Ah,
Right.
right 3, up 1. So I go right 3, up 1. 1 little, 2 little, 3 little, 1 little. 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 There you go. Let's shift it. Is that cleaner
Yeah.
than trying to get you guys to do mental math? Let's just do it that way then. To be honest, either way is fine. I always try to push you guys to do the other one because I always feel that every year that number sense kind of lacks a little bit. So I always thought that by picking out values that kind of help you guys to see why numbers move and how they manipulate on their own, it's kind of nice, but it's not the end of the world. And like I was saying later, like we were talking about, these a values, when we get to logarithms and exponential functions and trig values, these a values are always going to show how fast something is increasing or how slow something is increasing via the curves. It's the same idea when you get the trig functions. It's going to be how high up their frequent, or not frequency, their amplitude is, how far apart things are from the centers and stuff like that. It's a very common occurrence. If this was a negative, this would have been, 1, then a negative 2, a negative 4, a negative 6. That meant the original function would have done this. It would have been looking at it on the bottom side. And you would just move them accordingly. Okay? Does that make a little bit of sense? So let's do, well, I don't know. Not much time. Let me pick out a couple of problems. How many pieces of graph, how many graphs do you have left on the front right there? You got what, 4? 3? So, all right, let's do this. You have 6? Oh, yeah.
The new book?
Yeah, the old book has really good ones too, but we've done everything else on the, except for one section. Let's see. Let me make a decision.
Four for